Hello students, let us continue our discussion on the application of the concepts of thermodynamics of open systems in phase equilibrium, where we have seen how to connect the concept of chemical potential in predicting the temperature dependence of phase stability. So this entire analysis was dependent on this particular equation that we have derived earlier, and we find that simply because mu depends on temperature at a given pressure and the slope of the plot of mu versus T is different for different phases of a pure substance. Therefore, it is very easy to predict the stability of one or more phases at a given temperature and pressure of the system. We next take up the question of pressure dependence of phase stability. And once again, what we are going to do is, I'm going to find out the dependence of mu on pressure keeping temperature constant at a given temperature rather. So this particular equation that we have already found, that tells me that now I should look at this portion of it, and therefore I would be interested in understanding the value of this derivative, that is del mu del Pt, which is nothing but the molar volume of the substance. Now, if a given substance can exist either as a solid phase or a liquid phase or a gas phase, then I understand that the mu versus the value of mu as I increase pressure at a given temperature will be very much dependent on whether the phase is a solid, liquid or gas. And this is simply because at a given temperature, the molar volume of the solid, or any given temperature, the molar volume of the solid is always less than the molar volume of the liquid and is much less than the molar volume of the gas. Therefore, I'm going to use this understanding as before to analyze how stability of a given phase of a pure substance depends on pressure. Let me first take the instance of melting of solid. And this is the picture that is available in the standard textbook. So what I have here is, once again, I am plotting along x-axis the temperature at which my experiments are being carried out, and this is the chemical potential at a given pressure. So in my first set of experiments, this line corresponds to the variation of mu as a function of temperature at some low pressure value P1, and this is the corresponding variation of the chemical potential of the liquid phase at the same temperature. What I can do is, if in order to understand the pressure dependence of phase stability, I will now carry out another set of experiments whereby I will be carrying out the same exercise, that is plotting of mu versus temperature at a higher value of pressure, some other P2. Now what will happen? I will, at every temperature of this plot, if I consider this particular temperature, this is the value of mu of solid at a lower pressure P1. What would be the value of the solid if I am looking at the same temperature but at a higher pressure? I understand that then the value of mu would be higher. That is because mu increases with increasing pressure. Molar volume is always a positive quantity, and therefore mu would always increase with increasing pressure, and therefore this is where I will find the value of chemical potential of the solid at the given temperature marked here. If I repeat this exercise, then the line that I have got for the solid at a lower pressure will translate to this particular line at higher pressure, because for each value of temperature, mu will undergo the same amount of shift to a higher value, and therefore I am going to get a nearly parallel line between the low pressure plot and the high pressure plot. Similarly, I can draw the same pictures for the liquid, and so this is my solid graph, this is my liquid graph. But in the case of liquid, I understand that Vm of solid in general is less than Vm of liquid, which means that at any given temperature, when I am, let us say I am at this temperature, and I would like to know that at this temperature, if this is the value of mu at low pressure, what is going to be the value of mu at this temperature but at a higher pressure? I understand once again the value would be much higher and it would be located somewhere here. For every such temperature, there will be a much larger shift in the value of mu at the higher pressure, and therefore the new liquid graph is now going to be this line, which is now shifted by a much bigger amount than the pair of lines that I had for the solid phase. So this is the most common instance that we see in nature. But this happens when I have the molar volume of the solid less than molar volume of the liquid. Now, what is the consequence of this? The consequence is that initially at lower pressure, this was the point where the solid curve and the liquid curve were crossing each other. So this is the value of the melting temperature at the lower pressure. Now, because of the shifting of the solid curve and a greater shifting of the liquid curve at higher pressure, what has happened now? Now I find that mu s equal to mu solid equal to mu liquid, this condition is encountered at some other temperature which is much higher than the previous melting point. And therefore, we conclude that the melting point of the solid would increase with pressure when the molar volume of the solid is less than the molar volume of the liquid. But is this the only way that we encounter melting of solid in nature? The answer is no. We also find that there are instances where the molar volume of solid may be greater than the molar volume of the liquid. And this is a demonstration of that particular situation. We will see what will happen under such condition, but let me give you the observation first. Here, the melting point would decrease with pressure. That is because now the shift of the chemical potential value for every temperature is higher when we are considering the solid phase compared to the shift in the liquid line plot as I go from lower pressure to a higher pressure. And the most common example of this happening is the melting or fusion of ice into water, which happens normally at 273 Kelvin, that is 0 degree centigrade, and 1.0 bar. Now, for this change in phase, that is going from the solid phase into the liquid phase, we ask the question that what would be the effect of increasing pressure on the melting point of ice into water. In order to do that, let us say that I have taken up this exercise that I am going to increase the pressure from 1.0 bar to 2.0 bar at 273 Kelvin. And I am interested in finding out the effect of such increase in pressure on the chemical potential of the ice water system. So this is how we understand the effect. So what we are going to do is, we are going to start the exercise by plotting mu versus T at the lower pressure 1.0 bar. So this is going to be the typical variation of mu with respect to temperature at 1.0 bar. Now if I plot the same quantity with respect to the liquid phase, this purple dashed line shows how mu is going to change with respect to temperature at the pressure 1.0 bar. Therefore, by definition, the melting temperature is where the two curves have intersected, and here we have marked that temperature as T equal to Tm. Now, when we go and try to carry out the same exercise at 2 bar, there are certain things that we must take into consideration. We understand that at every temperature T, what is going to be delta mu T? That is going to be molar volume multiplied by delta P. So I have got this expression just by realizing that del mu del P T, that is equal to molar volume, and the molar volume in the case of a solid or a gas is a very weak function of pressure, and therefore what I can do is I can write this as d mu T, that would be equal to Vm into dP under that constant temperature condition. If I now integrate, I can take the Vm out from the integration simply because Vm is nearly independent of pressure, as both the liquid and the solid phase are highly incompressible, and therefore I can approximately write that delta of mu T, then it is going to be equal to Vm into delta P. Now what is Vm? That is the molar volume. So by definition, I can write this as m by rho into delta P. So what is m by rho? M is the molecular weight of my pure substance, and rho is the density of the phase that we are talking about. Now please let us go back and see the consequence of writing the delta mu T, that is the shift in the value of chemical potential at a given temperature as we shift the pressure value by delta P. Now what we have is, for water, my molecular weight is known from the literature. I am using SI units, and therefore for delta P is equal to 1.0 bar, as I go from a lower pressure of 1 bar to a higher pressure of 2.0 bar, I understand for ice delta mu T is going to be some value, and this value is given by delta mu ice, that is equal to plus 1.97 joules per mole. And as a result, I see at the higher pressure now compared to the lower pressure curve, I now have the variation of mu by T, mu versus T, given by this solid black line, where it shows that at every temperature, the value of mu of the solid phase is increased by 1.97 joules per mole. Now think about the water phase. There, the molecular weight is the same, but the density is different. So if I calculate the delta mu for water and plot mu versus T, this purple line is going to show me the change in behavior of mu in liquid water. Here I find that there is a much lower change, because if you calculate delta mu water at a given temperature, you will find that this has a much lower value. Now, what is the consequence here of this observed change? I find that now the melting temperature has gone to a lower temperature value, and therefore I have a decrease in melting point of ice on increasing pressure. Now my question is, what happens if I look at the old melting temperature, the original melting temperature of ice? At this higher pressure, since this is where the mu of ice is equal to the mu of water, now if I look at this particular temperature, now I have two different values of mu, one for the ice phase and another one for the water phase. Now, which phase has a lower chemical potential? Obviously, the liquid water has a lower chemical potential. Therefore, at Tm, at this very high pressure, what would be the most stable phase of the substance? Obviously, the liquid phase, which is characterized by a lower chemical potential, is going to be the more stable phase. And therefore, now when you are working at this high pressure, 2.0 bar, at 273 Kelvin, the most stable phase of your substance, H2O, is liquid water. But when you were at a low pressure, it was at 273 Kelvin that both ice and water could coexist in equilibrium. Now, moving over, therefore, we say that now I find that water is more stable at T equal to Tm if I raise the temperature to pressure to 2.0 bar. Now let us move over and use the same kind of concept to understand the phase stability of a pure substance when I have the vaporization. Now, in the case of vaporization, what kind of phase transition or phases that you are talking about? We are talking about the transition from the liquid phase to the gas phase, and whether these two phases, the liquid and the gas phases, can coexist in equilibrium. Now, while I think about it, once again, let me highlight the fact that the molar volume of gas is much, much higher than the molar volume of the liquid. Therefore, this is expected to result in a very large decrease in the boiling temperature. This is how I explain this. Once again, I will plot mu as a function of temperature at a lower pressure. If I do that, then this is the plot for the liquid phase at lower pressure, and this is the plot for the gas phase at a lower pressure. Now, if I want to mark the boiling temperature, it is this temperature at which the mu of gas under the given condition of temperature and pressure becomes equal to the mu of the liquid. Now, I will think of what happens when I increase the pressure. When I increase the pressure, then instead of these previous curves, now I'm going to have a high pressure curve for the liquid like this, and a high pressure curve for the gas that is given by this line. And now you understand that the new point where the two phases can be at equilibrium is located at this condition, which is marked by a much higher temperature. And therefore, I understand that there is a large increase in the boiling temperature with increasing pressure. Now, therefore, at higher pressure, the liquid will boil at a much higher temperature. Now, I understand here that because of the difference in the molar volumes of the liquid and the gas, as I went from a lower pressure to a higher pressure at a given temperature, the shift in the mu versus T plot was small for the case of liquid, and this shift was much higher for the gas. And this is the root cause as to why my system is now exhibiting this large increase in the boiling temperature with increasing pressure. And therefore, I can argue that if I want to find out these relative changes, I find that at this temperature, boiling temperature, which is 373 Kelvin, if I carry out the vaporization of liquid water by changing the pressure from 1 bar to 2 bar, then I will have for the liquid phase, the shift would be given by 1.87 joules per mole, but the water vapor, the shift will be much higher, that is 3.05 joules per mole. And that is what will result in having a much higher boiling temperature for the liquid at 2.0 bar. Now, as you see, at the old boiling temperature, that is 373 Kelvin, what is the most stable phase now? I understand that liquid water now is characterized as the most stable phase of water when the total when the pressure of the system is 2.0 bar. And this is why. So, I am going to look at the behavior of the high pressure curve. So, this is the liquid pressure curve, and this is a liquid phase curve, and this is the gas phase curve at high pressure. Now, at this temperature Tb, which is less than the new boiling temperature, what is the value of mu for the liquid phase? It is this value. And what is the value of the mu for gas phase? It is this value. So, which one has a lower value? The liquid phase has a lower value. Therefore, if I am at 2.0 bar pressure, in that case, what will happen is at 373 Kelvin, water will still remain in the liquid phase. And if I want to boil it, I'll have to take it to a higher temperature as marked by Tb prime here, and that is when it will start boiling. Now, the point is, can I see some application of these concepts in real world problems? The answer is yes. And the applications, especially for the decrease in melting point with pressure in the cases such as water, is very widespread. So, if I take the pair of ice and water, you might have come across people skiing on ice surface, and this is possible simply because when you are applying pressure using the ski blades when you are skiing, the ice surface, at the surface of ice, the pressure is high, and therefore the melting temperature would now decrease. Therefore, if you are skiing at 273 Kelvin, right below your skiing blades, the temperature is, the pressure is very high, and the melting point there is much lower, which means that at that temperature, it's not ice, it will melt into water. That will act as a lubricant under your ski blades, and you will be able to ski and perform all those astonishing acrobatics as you see in this video. Now, there's another extremely interesting case which relies on the change in melting point as mountains are formed. Now, there are only 14 mountains on the Earth's surface above water that are more than 8,000 meters in height. So, this once again, very, very unexpectedly, is a result of the fact that the melting point of the Earth's crust changes as the mountain grows and exerts a very high pressure on the earth crust right below it. We will come back to this instance later, but let me take a quick look at what we are going to do in our next lecture. We are now going to talk about the effect of variation of both temperature and pressure when I have a pure substance for which two phases are coexisting in equilibrium. And I need to understand how this equilibrium can be perturbed by changing both temperature and pressure. Thank you.